Welcome to Lecture 7b, which is just an extension from 7a. And this is tangential plane and linear approximation to curved surfaces. This material is from section 15.6 of the text. There is new material in here. However, this more or less is just an add-on to what's in the textbook. The objectives are to estimate how the output value of a multivariable function varies with respect to small changes of variables about a reference position or a point in absolute and per unit terms. The concepts or visualization skills we'll be considering here are what we consider the multivariable Taylor expansion. So this is an extension to what you learned about Taylor series expansions with one variable. We now extend it to multivariables. The derivation of the tangential plane. So now we basically delve into the mathematics. Something we call a Hessian matrix. We will not use it, but it basically is a matrix that's used to establish the critical points. That is, where are local maxima and local minima, or even inflection points, which are called saddle points when you're dealing with surfaces. And then per unit calculations, which in fact sensitivity analysis, as alluded to in the previous lecture, that is lecture 7a. Again, just a note, we briefly discussed tangential planes when we introduced multivariable differentiability in lecture 4b. As usual, the second slide just is a summary of the various slides, so we'll just move on. All right, so just a quick review in terms of a Taylor series expansion of a function describing a curved line. So what we're trying to do is approximate a curved line at a given point. So this would be some position xy, which is AB on the xy plane. And so the Taylor expansion would be that f of x is f of a plus the derivative of f with respect to x evaluated x equals a times x minus a. And if we carry out this to higher order terms, then we'll have the next most significant term will be the second derivative with respect to x multiplied by 1/2, x minus a squared, and so on. So the critical points of a function y of x are determined by setting df dx equals 0 and solving the resultant equation for x. The second derivative test is used to determine if a critical point is a local min, a local max, or an inflection point. Of course, this assumes that the second derivative exists. If it doesn't, then you would have to basically go to higher order derivatives to determine if there's a max or a min. So the first order approximation to the curved line would be taking the Taylor series expansion and only redating the linear terms. So that means y is equal to f of a plus df dx evaluated at x equals a times x minus a. The picture on the right basically shows how we establish the tangent line, which is in fact the red line, which represents the first order approximation. And so in the limit, we basically are just looking at the behavior of the curved line at the point P for very small changes taking place, which means it is a straight line, and that straight line is in fact described by the equation at the bottom left. All right, so now let's basically extend the notion of Taylor series expansion of a function to a curved surface. In this case, the points of interest would be some x, y, z is equal to a, b, c. So that would be in a three-dimensional space. So in this case, if we're interested in looking at the nature of the function about a point, that is at a, b, c, we would expand it in a similar fashion as we did for the case of one variable. But now we have more derivatives to consider. We have all these partial derivatives. And so in this case, basically, when you expand to first order, you have a partial f with respect to x times x minus a and a partial f with respect to y times y minus b. When you expand to second order, that means you have to take second derivatives. So now consider all the possible combinations in terms of how you can take second derivatives. So you can take a second derivative of x twice, you can take a second derivative of y twice, and you can take mixes. So you could take derivative with respect to y followed by derivative with respect to x, or the other way around. We mentioned in an earlier lecture that second derivative with respect to y and x is equivalent to second derivative with respect to x followed by y if certain conditions on the function basically are maintained, particularly continuity. And so that means that in effect, the two terms can be grouped together and added because they're exactly the same. In fact, you'll notice here, what is the difference between this term and this term? No difference, other than the ordering of the multiplication of these two here. So it's y minus b times x minus a, but that's equivalent essentially to the product of x minus a times y minus b. So you have your first order terms, which are these. This is a 0th order term, and these are all second order terms. All right, now it's useful to take what we've just written and let's put this in matrix form, because we mentioned in a much earlier lecture that in fact you can take dot products, and write them out basically as vectors, or you can basically write them in matrix form. So if you look at this expression now, you'll notice I've written it out as this is a constant c. This constant c mirrors the value of the function evaluated at a and b. And so this is now the dot product between a vector and another vector. The vector d is going to be composed of an x component of x minus a and a y component of y minus b. And the gradient we know has this form. If I take a row vector, okay, if I take this as a vector, and I take this as a dot product, this is a vector and a vector, then this basically will give you a scalar, which is equivalent to the expression we had on the previous page. Now in this case, the second order term, we can basically use this expression to get the second order terms on the previous page. However, we have to make a slight change. And if you'll notice here, for instance, I've got star, which basically is meant to mean multiplication. And so we're basically now looking this now in matrix form. So D would be basically a row, and D transpose would be a column. And H would be basically a matrix, which includes all those partial derivatives that we looked at in the previous slide. So there's the second derivative with respect to x, xy, yx, and the derivative with respect to y taken twice. This thing is called the Hessian matrix. Now, as an exercise, if I take D, which is this, times this matrix, times D transpose, I'll get the same expression as you saw on the previous page. So this is in a much more compact form, and it's much easier to work with in many cases. So what about the critical points in this case? In other words, where will I expect to see local min, local max, and something I called a saddle point, which is the 2D equivalent of an inflection point in 1D? Well, we basically, by setting these partial derivatives to 0 and solving the resulting equations, we can determine the critical points. And the second derivative test is used to determine if the given critical point is a local min or a local max or a saddle point, assuming the second derivative test gives conclusive results. The second derivative test is buried in the details of the Hessian matrix. It is a symmetric matrix, right? Symmetric meaning if you look at this side and this side are equivalent to each other. So this is a symmetric matrix. But it's not discussed in this course, but is the subject of section 15.7 of the textbook. It's no longer part of the course because we introduced reading week, and that meant something had to go. And the textbook doesn't really do justice to the topic. It's best treated on its own in a more expanded fashion. And so basically that's why this was left out. So you don't need to know anything about taking second derivative tests. It's just here for your interest. All right, so let's basically look at taking to first order. So we take the previous results and look at first order. And so we only retain these two terms here. All right. So this is C, that's the value of Z that we're interested in, A and B. And so this is basically the first order expansion. All right, now we're going to basically wanting to determine what the tangential plane is. And since it's linear in X and Y, you would assume this starts to look or has a resemblance of a tangential plane. So what we're going to do is rearrange terms. We're going to bring the C over to this side. That's this, what you see here, and we're left with just this expression. And now what we do is we take all things which are of a constant nature, which means the C's, the A's, and B's, and bring them over to the right-hand side, which is what you see here. And everything involving the variables, X and Y, is on this side. So we have a Z, we have an X, and we Y. If you look at this, you'll notice that all the items marked in yellow These are constants because we're going to evaluate this at A and B, at A and B, at A and B, and A and B, and A, B, and C's are all constant. So what is this? This is the equation of a plane. This is the equation of the tangent plane at the point A, B, C. All right, an alternative method for determining the equation of the tangent plane, which is basically described in the textbook. Let's look at this. Let points of a contour C on the surface fxy, which is the contour that you see here. Then the surface is given in implicit form, be defined by a position vector, which is a parameterization variable t, x at t, y at t is z t. Hence, if you substitute basically into here for x as function of t, you're mapping out basically points on the surface along a line. Okay, so that point represents points on the contour lie on the surface. So now the vector tangent to the contour lying on the surface is just taking the derivative with respect to the parameterization variable, which is what I've done here. So that's the tangent vector that we're looking at here, r prime t. So next thing we do is fix a point P naught t, P naught at ABC, which is this point here, on the surface, such that FABC equals 0. I mean, this is basically the equation that satisfies the notion that this point is lying on the surface. So the vector tangent to any contour C that passes through this point and also lies on the surface is orthogonal to the gradient of the function at the point ABC, as shown in Lecture 6 and shown in the figure below. So the gradient is perpendicular to the surface, okay? And that line basically, the tangent line basically lies on the surface, so the line and the gradient are perpendicular to each other. The tangent vectors associated with different contours C all passing through the point P naught lie on the same tangent plane. So this gives you an example. Here's a contour. This will be parameterized differently than this one and this one. We can define tangent vectors for each one of these lines lying on the surface. But if you look at each one of these lines, these basically would lie on this tangential plane. Okay, so that's another way basically of visualizing the creation of the tangent plane. So next step is do the calculations. So consider the position x, y, z at any point on the tangent plane, right, arbitrary point, and create the vector between this point and the point ABC. That's the point of interest where the tangent plane just touches the curved surface. Then we know that a vector that's produced by taking the difference between the x and the a, y, and b, and c. This is some arbitrary vector. If we dot product with the normal and enforce the condition of perpendicularity, which is basically the definition of a tangential plane, right, then that dot product must be equal to 0. All right, so now what we do is we just take this and work it out and simplify. And so what we'd like to do is to take all expressions involving the variable x, y, and z to be on the left side and everything else on the right-hand side. So here you are. Here's a component with x, with y, with z, and everything on this side involves constants. All right, the next thing we're going to do is write the expression in explicit form. So the function itself. So fxyz was equal to 0, but that's like saying fxy minus z equals 0. So this and this are equivalent to each other. This is an implicit form. This is an explicit form. All right, so if we're going to take df by dx here, we do df by dx on this side, and we'll get basically df dx partial. If you tf dy, right, then we'll get df dy partial. If we take df by dz, then you get minus 1. So now what we do is backwards substitute. We put this, and this in for df dx, df dy, df dz, and we end up basically with this expression on the left-hand side, which would be here, and this expression on the right-hand side. So this is exactly the same function that we described when we looked at it from a point of view of a first-order approximation to Taylor series expansion for two variables. All right, so now let's look at some sensitivity analysis and per unit calculations. So we use the Taylor series expansion to first order. And so all I'm doing now is I'm bringing the c constant over to this side. So now z minus c is equal to this expression here. I'm going to let delta z be equal z minus c, delta x being x minus a, and delta y being y minus b, in which case this expression here becomes delta z partial x, partial y. All right, so now you would say, okay, this is the actual expression, which we call sensitivity analysis. Small change in x, small change in y. Do these calculations at the point of interest. Gives you the change in the output, delta z. So, but these would be in values which have units. If we want to convert this into something with no units, then the first thing we'll do is we're going to divide dz by z. And if we're going to do it on the left, we do have to do it on the right. So you'll notice a z is here, a z is here, and a z is here. So this has no units. All right, so what about dx and dy? Well, a little trick. You take dx, divide by x, and multiply by x. Now this is in per unit form. For dy, you divide by y and multiply by y. It's still dy, but now this is in per unit form. The x and z here basically are the values that you choose as your base values. We were basically given an operating point, and that operating point would be at a, b, c. X was a, y was b, and z was c. So in that case, basically the things in blue are just replaced by the equivalent scalar constant values, which then gives you the results that you see over here. And so these are constant values that you can substitute. These are constant values you can substitute, and these are now per unit variables. All right? Sometimes we just basically use this approximation that delta z equals dz, in the limit. So it can be used either way. Okay, so the last slide basically is an example. So you're given a body mass index for an adult human, some function of two variables, w and h, where w is the weight measured in kilograms and h is the height measured in meters. So these are basically units, okay? So part A asks you to use differentials, dw and dh, to approximate the change in the body mass index when weight increases from 55 to 56.5 kilograms and height increases from 1.65 to 1.66 meters. Part B, which produces a greater percentage change in the body mass index? A 1% change in the weight at a constant height, or a 1% change in the height at a constant weight? All right, so we'll start with part A. So part A basically requires that we determine the partial derivatives with respect to w and respect to h, which is precisely what I've done here. If we take this function and take the partial derivative with respect to w, we end up with this value. And we have to evaluate it at the given height and body weight. And so we substitute the values in this case only h plays a role, and we end up with 0.37. Similarly, we have to take the derivative with respect to the height, and then substitute in for the value of the weight and h, these are the values again, and you get minus 24.49. So we can write out basically in non-per unit form that dB is equal to this, dw, plus this times dh. You can substitute the numbers in and you get 0.31. All right, now let's take the same expression and put it in per unit form. All right, so in this case what I'm doing is I'm going to divide through by b on both sides. Okay, so here, for instance, this expression, if you divide through by b, you'll have dB by b. If you divide bw by b, there basically is the resultant of 1 over b, and this is basically going to be the resultant of 1 over b over here. Okay, so now basically you take what the expressions that you already developed, bw, which is here, and bhw here, and you substitute those here. Here they are, 1h over squared minus 2 over h cubed, and you simplify. H squareds basically cancel out, and you end up with a w. And here the h squared over h cubed, these are 1 over h, but the w's cancel. And you're left with dw over w, which has no units, minus 2 times dh over h also has no units. And so now we come basically to the last part, which is part B. 1% change in w, which means dw over w is 0.01, produces a 1% change of the same sign as b. So db over b is 0.01, okay? A 1% change in h, which is 0.01, which would be here, produces a 2% change in b of the opposite sign, minus 0.02. There's a 2 there, and there's a minus. So this goes from minus 0.01, from 0.01 to minus 0.02. So that basically concludes Lecture 7B. Thank you for listening.